Hello everyone, welcome back to the Smart Grid course. In today's lecture, we are going to understand one of the most important topics of this course, the smart grid transition. Electricity has become an essential part of our daily lives. From our homes and industries to hospitals, communication system, transportation, and even agriculture, almost every activity depends on a reliable supply of electrical energy. However, the electrical grid that we use today was designed several decades ago. At that time, electricity demand was much lower, renewable energy sources were almost absent, and consumers only used electricity, they never generated it. Today, the situation has completely changed. Electricity demand is continuously increasing. Renewable energy sources like wind and solar are becoming more common, and many consumers are also becoming electricity producers. Because of these changes, the traditional power grid is no longer sufficient. This has led to the development of a modern electricity network known as the smart grid. In this lecture, we will understand why this transition became necessary, how smart grids differ from conventional grids, and what technologies make them intelligent. So let's begin by understanding why we actually needed this transformation. So an electric grid is simply a complete network that connects the place where electricity is generated to the place where electricity is consumed. So it includes generating stations, transformers, transmission lines, distribution system, and finally the consumer. We first need to understand how the traditional electric grid works. Once we know it's working, it becomes much easier to understand why the smart grid was introduced. So, if you talk about the meaning of electric grid, so electric grid is a network of synchronized power providers and consumers connected through transmission and distribution lines and operated by control center. So, an electric grid is simply a complete electrical network that connects the place where electricity is generated to the place where electricity is consumed. It includes generating stations, transformer, transmission lines, distribution system, and the consumers. So, in the figure, the first block representing the power plant. So electricity is generated in power plants such as thermal power plants, hydroelectric power plants, and nuclear power plants. Regardless of the energy source, the final output of these plants is electrical energy. Normally, electricity is generated at a medium voltage level, generally around 11 kV to 25 kV, depending on the generator design. Then the second part is the step-up transformer. The transformer increases the voltage and reduces the current. Reducing current is extremely important because transmission losses are proportional to the square of the current. So this transformation can be in the AC or DC. Then after stepping up the voltage, electricity is transmitted through high voltage transmission lines. These transmission towers carry electrical power over long distances, from the generating station to the different regions, cities, and substation. The main purpose of this stage is to bulk power transfer with minimum losses. Once the electricity reaches to the receiving substation, it passes through a step-down transformer. Here, the voltage is reduced to a suitable level of distribution. This is necessary because consumers cannot safely use transmission level voltages. The distribution network further reduces the voltage according to the type of consumer. So generally there are three types of consumers are available. So first one is the industrial consumer. So in industrial consumers, Generally, factories and manufacturing plants are come. Then in residential consumers, uh, apartments and housing societies are come under this category, and domestic consumers, referring to the individual homes where electricity is used for lighting, fans, televisions, refrigerators, and other household appliances. Although these consumers have different load requirements, all of them receive electricity through same basic grid structure. In the traditional grid, electricity always flow in only one direction. The power plant generates electricity. The electricity travels through the transformer and transmission lines. Finally, it reaches to the consumer. The consumer only uses electricity. The consumer cannot send electricity back to the grid, even if they generate power using rooftop solar panel. So, this one-way power flow was perfectly suitable when electricity generation was centralized. However, with the increasing use of distributed renewable energy sources, this has become one of the biggest limitations of the conventional grid. Now that we understand the limitation of the conventional grid, let's see how the National Institute of Standard and Technology defines a smart grid. So, as per the NIST, a smart grid is a modernized grid that enables bidirectional flow of energy and uses two-way communication and control capabilities that will lead to an array of new functionalities and applications. So we will try to understand the meaning of each and every word. So first one is the modernized grid. So a modernized, the word modernized simply means an upgraded version of the traditional electric grid. Notice that the smart grid is not a completely new power system. We still have generating stations, transmission lines, substation, transformer, and consumers. The difference is that modern technologies such as communication network, sensors, automation systems, smart meters, and intelligent controllers are added to the existing electrical infrastructure. So instead of replacing the entire power system, we make it smarter by integrating digital technologies. Then the second word is the bidirectional flow of energy. This is probably the most important feature of the smart grid. In the conventional grid, electricity always moves only in the one direction. It started from the power plant and finally reaches to the consumer. The consumer had only one rule to consume electricity. But today, many homes, industries, and commercial buildings have rooftop solar panels. During the daytime, they may generate more electricity than they actually need. Instead of wasting this extra electricity, it can be supplied back to the utility grid. This means electricity can now move from the grid to the consumer as well as from the consumer back to the grid. So this is called the bidirectional energy flow. Now look at the small diagram at the bottom. The upper illustration represents the old grid. Notice that all the arrows are moving only in one direction. This clearly shows that the electricity travels only from the utility towards the consumer. Now observe the lower illustration. Here you can see arrows moving in the both direction. So this represents the smart grid where electricity can flow both ways depending on the system's operating condition. The third word is the two-way communication. So this is another feature of smart grid. Now you can think about the traditional grid. The utility company sends electricity to your home, but it has almost no information about what is happening inside your electrical system until someone reports a problem. For example, if there is a power outage, the utility often knows about it only after consumers call the customer service center. In a smart grid, the situation completely changes. Smart meters, sensors, intelligent electronic devices, and communication network continuously exchange the information between the utility and the consumer. The utility can monitor electricity consumption in real time. Similarly, smart meters can instantly report faults, voltage fluctuation, power interruption, and energy uses. This is why we say communication takes the place in both directions. Then the next word is the control capabilities and new functionalities. So in smart grid, communication alone is not sufficient. The smart grid also should be to take intelligent decisions automatically. For example, suppose a fault occurs in one distribution feeder. Instead of disconnecting the entire area, the smart grid can identify the faulty section, isolate it automatically, and continue supplying electricity to the healthy sections. Similarly, it can automatically balance electrical load, manage renewable energy sources, schedule battery storage, and improve overall system efficiency. These intelligent operations are referred to as new functionalities and applications which are not possible in the conventional electrical grid. Now that we have understood why a smart grid actually is, the next question is how it is different from the conventional electrical grid in practical terms. So, to answer that, let's move to the next slide where we will compare the conventional grid and the smart grid feature by feature. So, let's start with the first parameter, power flow. In the conventional grid, power always flow in one direction. Electricity is generated at the power plant, transmitted through high voltage transmission, distributed through substation, and finally reaches to the consumer. Once the electricity reaches the consumer, the process ends. The consumer only uses electricity and cannot send it back to the utility. Now look at the smart grid. Here, power flow is bidirectional. This means electricity can flow from the utility to the consumer. And if the consumer generates electricity using rooftop solar panels or other renewable sources, the excess electricity can also be supplied back to the grid. This concept is known as the bidirectional power flow, which we discussed in the previous slide. Then the second point is the communication. In the conventional grid, communication is either absent or very limited. The utility mainly supplies electricity, but it receives very little information from the consumer side. For example, if a transformer fails or there is a power outage, the utility usually becomes aware only after consumers report the problem. On the other hand, the smart grid uses two-way communication. Smart meters, communication network, intelligent electronic devices, and sensors continuously exchange information between consumers and utilities. Because of this continuous communication, the utility always know the condition of the electrical network. Then the point 3 is the monitoring. In a conventional grid, monitoring is mostly manual. This means faults are often detected by some delay. Engineers need to inspect substation, feeders, and equipment physically or collect information periodically. In a smart grid, monitoring is performed continuously using intelligent sensors and automated monitoring system. The system continuously measures voltage, current, frequency, power flow, and equipment condition in real time. As a result, problems can be identified much easier. Then the next point is the fault detection and restoration. In a conventional grid, locating a fault takes considerable time. Suppose a transmission line breaks during heavy rain. Maintenance engineer must first identify the fault location, travel to the site, inspect the equipment, and then restore the supply. This entire process may take several hours. In a smart grid, intelligent sensors immediately detect abnormal condition. The control center receives the fault information almost instantly. Many smart grid systems can even isolate the faulty section automatically while continuing power supply to healthy areas. This significantly reduces outage duration and improve the reliability. Then the point 5 is the consumer participation. In the conventional grid, consumers are passive users. They simply consume electricity and pay their electricity bill. They have no active role in grid operation. In the smart grid, consumers have become active participants. Using smart meters and rooftop solar system, consumer can monitor their electricity uses, manage energy consumption, participate in demand response program, and even export excess electricity back to the utility. Such consumers are called prosumers because they are producers and consumers of the electrical energy. So far, we have understood the limitations of the conventional power grid. But the question is, why do we need a smart grid? There are four major reasons. First one is the rapid increase in electricity demand. Second one is the urbanization and industrialization. Third one is the large scale integration of renewable energy sources and the increasing adoption of the electric vehicles. The traditional grid was designed for one-way power flow and predictable demand. Today, demand changes every minute, renewable energy is intermittent, and EV charging creates sudden load variation. Therefore, the conventional grid alone cannot maintain power quality and reliability. This is why we need a smart grid equipped with sensors, communication system, automation, and artificial intelligence. Now let's discuss the first major need for a smart grid: managing increasing electricity demand and integrating renewable energy sources. As electricity consumption increases due to industries, urbanization, and modern electrical appliances, the conventional grid faces challenges like transformer overloading, voltage fluctuation, and higher transmission losses. At the same time, renewable energy sources such as solar and wind are being connected to the power grid. Although they are clean energy sources, their power generation is intermittent because it depends on weather conditions. For example, solar panels generate less power on cloudy days, and wind turbines depend on the wind speed. The smart grid solves this problem by continuously monitoring both electricity demand and renewable energy generation in real time. Using smart sensors, communication system, and intelligent control, it maintains the balance between power generation and power consumption, ensuring a stable, reliable electricity supply. A smart grid enables efficient utilization of renewable energy while maintaining the stability of the power system. Then moving to the second need. So another reason for adoption the smart grid is the rapid growth of electric vehicles. Now imagine if hundred of EVs in a city start charging at the same time during the evening. This sudden increase in demand can overload transformers and distribution lines, causing voltage fluctuations and reducing the reliability of the power system. The smart grid addresses this challenge through smart charging. It can schedule EV charging during off-peak hours, and even support vehicle-to-grid technology, where EV batteries can supply stored energy back to the grid during peak demand. Another key feature is load forecasting. The smart grid uses historical data, weather information, and AI-based algorithm to predict electricity demand. This helps utility plan for power generation efficiently, reduce wastages, and maintain a continuous power supply. The smart grid supports the increasing number of electric vehicles accurately while forecasting future electricity demand, making the power system more efficient and reliable. Then moving to need, the next important need of a smart grid is to improve the reliability of the power system through its self-healing capability. In a conventional grid, when a fault occurs, engineers first need to locate the fault manually, isolate the faulty section, and then restore the power supply. This process takes time and results in longer power outages. In contrast, a smart grid uses smart sensors, intelligent electronic devices, and automated switches to detect faults in real time. As soon as fault occurs, the system automatically identifies the faulty section, isolates it, and restores power to the healthy sections through an alternative path. This process is called self-healing, as the grid can recover from faults with minimal human intervention. So, this self-healing improves the reliability of the power system by reducing outage duration, minimizing power interruptions, and ensuring a continuous electricity supply to consumers. Along with the improving reliability, smart grid also provides real-time monitoring of the entire power system and helps maintain power quality, which we will discuss in the next slide. In a conventional grid, the utility receives limited information about the network, making it difficult to detect problems quickly. However, in smart grid, devices such as smart sensor, then phasor measurement unit, and SCADA system continuously monitor important parameters like voltage, current, frequency, and power flow in real time. This allows operators to identify abnormalities immediately and take corrective actions before they become major faults. The smart grid also helps to maintain power quality by detecting issues like voltage fluctuation, frequency variation, harmonics, and power interruptions. It automatically controls the system to keep electricity supply stable and reliable. Real-time monitoring enables faster decision-making, while improved power quality ensures the safe and efficient operation of electrical equipment. Another major advantage of the smart grid is improving operational efficiency and effective asset management. In a conventional grid, equipment such as transformer, transmission lines, and circuit breakers are often maintained at fixed intervals, even if they are operating normally. This increases maintenance cost and sometimes fails to prevent unexpected failures. The smart grid continuously monitors the health of these assets using smart sensors and communication system. It can detect early signs of problems, allowing utilities to perform predictive maintenance before a fault actually occurs. This not only reduces maintenance cost but also increases the life of electrical equipment and minimizes unexpected outages. So, by continuously monitoring grid assets and enabling predictive maintenance, the smart grid improves efficiency, reduces operational costs, and ensures reliable system performance. Now, one of the biggest changes introduced by the smart grid is the consumers are no longer just electricity users. They can also become electricity producers. For example, A house with solar rooftop panels can generate electricity for its own use. If excess power is generated, it can be exported back to the grid, benefiting both the consumer and the utility. Another important component is the smart meter. Unlike conventional meters, smart meters record electricity consumption in real time and automatically send the data to the utility. This eliminates manual meter readings, provides accurate billing, and allows consumers to monitor their energy uses through mobile apps or online portals. The smart grid empowers consumers by enabling two-way energy flow, promoting renewable energy generation, and providing better control over electricity consumption through smart meters. Another important feature of the smart grid is the demand response, which helps to balance electricity demand during peak hours. Instead of increasing power generation, the utility encourages consumers to shift non-essential loads such as EV charging or washing machine to off-peak hours through time-based electricity pricing. This reduces the load on the grid and improves its overall efficiency. The smart grid also enhances smart security. Using smart meters, sensors, and advanced communication system, it continuously monitors the network and can quickly detect abnormal conditions such as electricity theft, unauthorized connections, or cyber attacks. This allows utility to take immediate corrective actions and ensure a secure and reliable power supply. Demand response optimizes electricity consumption during peak demands, while advanced monitoring improves the security and reliability of the power system. The final need for a smart grid is to create sustainable, secure, and future-ready power system. As the share of renewable energy sources like solar and wind continues to increase, the smart grid helps integrate these clean energy sources efficiently, reducing dependence on fossil fuels and lowering carbon emissions. At the same time, the smart grid is designed to support future technologies such as EVs, battery energy storage system, microgrid, and smart cities. Its flexible and intelligent infrastructure allows it to adopt changing energy requirements without major modification. Another important aspect is the cybersecurity. Since the smart grid relies on the digital communication and automation, strong cybersecurity measures are essential to protect the grid from the cyber threats and reliable operation. Now let's look at the smart grid ecosystem, which shows how all components of a smart grid work together. At the center of the diagram is the smart grid, which acts as the brain of the entire power system. It connects power generation, transmission, distribution, consumers, renewable energy sources, and electric vehicles through a two-way communication network. Unlike the conventional grid, where electricity flows only from power plant to the consumer, the smart grid allows both electricity information to flow in both directions. This enables real-time monitoring, faster decision making, and automatic control of the entire network. For example, if electricity demand suddenly increases, the smart grid can collect real-time data from smart meters and sensors and analyze the situation and take appropriate actions such as adjusting generation, utilizing battery storage, or managing demand. Similarly, consumers with rooftop solar panels can send excess electricity back to the grid, making them prosumers instead of just consumers. The smart grid ecosystem integrates generation, transmission, distribution, consumers, renewable energy, and communication technology into one intelligent system, ensuring a reliable, efficient, and sustainable electricity supply. With this, we have understood why the smart grid is needed and how its different components work together. In the next session, we will begin with exploring the architecture and key components of the smart grid in detail.